Great. So let's get started. So as I already introduced ourselves, let me just jump right in. What we use Confluent Druid here at Confluent for is really to provide all the customers or engineers and the business really operational visibility into our cloud operations. And you know, uh, just to give you a little bit of background on what kind of scale we're talking about here is that the Confluent Cloud has grown quite a bit over the last 2-3 years. And it's now at the point where we are running thousands of Kafka clusters, thousands of Connect clusters, and KSQL DB clusters, which all provide us with a lot of important data points. We're running all 3 major cloud providers and in dozens of regions across all these different cloud providers, and most importantly, all these services are all multi-tenant, which means that we need to get very good visibility into how they operate to make sure that we provide all our customers the best possible service we can. So as you can imagine, throughout like the last 2 years, we've grown quite a bit. A lot of the telemetry data we generate from the cloud ends up in Druid, as you would imagine, since otherwise we wouldn't be here talking about this. And with that, like we've almost 3x our volumes in the last year. We're now ingesting about 3.5 million events per second. But it's not just about the data volume here. It's also the request load we're putting on the system. We're comfortable and we're also confident that we can support us in giving our customers a lot of visibility and building products on top of it, which is why we're now at a scale where we're putting quite a bit of load on the system as well. And I'll let Zoe talk a bit more about some of what we've done on the infrastructure side and how to optimize that and everything. But what I want to talk about first is talk more about how we use this and how this actually helps us in our day-to-day operations. And there's really 2 facets of this into how we use Druid across the organization. It really enables us to provide insights not just internally, but also to our customers. So let's talk a bit about some of the internal use cases. I mean, all the information we gather from all these services that we run, like we can get a lot of product visibility by leveraging all the data we have in our Druid cluster. But not only that, we can also build automation around it. So a lot of the automatic scaling and things like that we're now providing in Confluent Cloud that leverages some of the data that we collect in our services. From our services. And lastly, but not least, like a lot of this data also helps our engineers day to day in kind of running these operations and giving them the data they need to make informed decisions, whether that's from a product standpoint or like in helping them troubleshoot a lot of the issues. But the nice part about all this data we have is that it's actually also very useful to our customers, because our customers want to get visibility into into the services that we run for them. They'd like to understand how they're using their product. Like they may want to charge back their customers. We want to be able to provide them with APIs so they can get this data into their own system, so that they can get some insights into what is really driving some of their usage and how the product is faring. And that customer visibility is really something that we wouldn't be able to provide without some of the technology here. So let's talk a bit about some of the high-level architecture. It's it's pretty simple. We get a lot of telemetry directly from our Confluent Cloud services. We push that into Kafka. So we have metrics and events that we collect, and then effectively directly put that into Druid. And on top of that, we then provide some APIs that provide some abstraction and kind of help make this a little bit easier to use. But we can then build a lot of products on top of that, like either internal products for internal visibility or like products for our customers, including some of the monitoring and metering and all that comes with a cloud that you need in order to run a cloud operation. On top of that, we also have direct access to the raw data for a lot of the engineers and other users that might be interested in understanding things in more detail for things where an API might not be the most flexible thing. So let's talk a bit about some of the use cases. I mean, some of the products that we built using all this data. So the first and most obvious one, of course, is our cloud dashboards. All this data you see in your Confluent Cloud dashboard when you log in, that's all coming from this infrastructure. Our customers can directly see what's going on. They can understand their high-level throughput, their storage usage, not just for Kafka, but some of the other products as well. They can really understand what are the high-level data points that they need to make sure that that they're using the system as they expect, and understand if they're hitting any kind of limits. The next level is of course, they can drill into this a bit further and understand, okay, well, how am I using, let's say, given Kafka clusters? What sort of throughput am I seeing on the various topics? And they can do that directly, of course, but we've also built some other much more powerful tools using this data, which allows them not only to see, okay, which topics am I seeing data in, how much data am I pushing through the various topics, but what are the applications that are actually consuming and producing from? And all this topology of this stream data flow and rebuilding this entire graph of all the applications that are producing from into a topic and the application consuming into a topic, and rebuilding that graph is all powered by the same data we collect into Druid, and it makes it very easy for us to build up these charts in real time. It gives them the real-time visibility to understand how all their different applications connect in Confluent Cloud. Next, I mean, we also, in the diagram earlier, I forgot to mention that we also collect data from our on-prem customers. And so we can provide them the visibility they need using in our cloud product. And what this helps them with is that they don't have to worry about figuring out how to instrument their own services. We give them a very opinionated view of what they should be worrying about. And this helps not only our customers, we can alert them proactively if we detect any issues with the on-prem services, but it also helps our support teams, which also have access to this data, because oftentimes when, for most of our customers, when they go on site and try to help them, they don't necessarily have the data that they need to troubleshoot. And by enabling this upfront, they usually have some history that helps them identify how things have gone wrong when they try to help their customers. So speaking a bit more about these internal use cases, I wanted to talk a bit about our how we get operation visibility into the cloud, and what are the sort of things that we do, and how all this data helps us. Now we're not just collecting a lot of data just for the sake of having it. It's really about when we talk about this operational visibility, we have multiple levels, right? We may want to have the 10,000-foot view, which gives us the overview across all our different clusters, our entire cloud, understand how the product is faring, how our customers are using it. But then we also need the ability to really drill down into kind of the needle in the haystack type questions, like understanding where something might have gone wrong. And that's where we need all these different facets. And it's a bit high level. So I want to kind of give you some examples of what how we use this data and what we've been able to do with it. So just to give you some ideas, having all this data gives us the ability to decide on how important certain features are, right? Certain things that we wouldn't have been able to do before, for instance, is survey all the different partition sizes that may be across all our Kafka clusters, and understand what is the breakdown of what percent of topics are compacted. And having this information then helps us decide, okay, well, maybe we want to invest into supporting compacted topics for tiered storage, or how important is it to invest into these features based on how people are actually using the product. But the next one is fairly obvious is incident response. That's where some of the more real-time aspects really come into play. Is that it really gives us the ability to very quickly drill down and pinpoint where things might have gone wrong. And we have enough information that we can identify, let's say, how certain clients are buggy, or they might be responsive for certain request patterns, and then we may have the client versions attached to some of these some of this data, which then allows us to go back to our customer, like, okay, well, maybe this version is that exhibited some bad behaviors. You should switch to a more recent one, or it helps us identify things that we haven't seen before with certain clients, since we don't think there's many different Kafka clients out there that we don't necessarily have full understanding of. And it also helps us in our communication with our customers. We can go through this data, and maybe sometimes we have like request level data, which allows us to identify if certain customers are affected by timeouts, and then reach out to them, or be able to target some of the our response a bit better, and not have to look at everything all the time. And the last one is more general performance analysis. Having some of these details, this information really helps us understand the effects of various client settings when they interact with our Kafka workers. How does it affect response times? Having some of this data is very important for us to be able to do this performance testing outside of some test bed conditions. We do quite a bit of soak testing for some of these some of the new features, but at the same time, we also want to see how things fare in the real world, because sometimes our customers exercise the product in ways that we don't expect, and that's where it's important to have this kind of data. Now, it's not just about having a lot of data. It's also having the ability to expose one set of data in many different ways, right? I think that's where this this architecture and being able to leverage it is very powerful. Is that if we take the example of, let's say, the Kafka throughput data, so we can collect a whole bunch of metrics on Kafka throughput. It's a fairly simple data, but it can be used in many different ways. The first and obvious way is for metering. So we can break this data down by our tenant, by user, and then we can use that to derive their bill in Confluent Cloud. The next one is when we can break it down by topic and client, like you said before, and rebuild this like stream data flow graph, and expose that via the UI and the API to our customers, so they can get the visibility they need into their operations. And the same data, again, we can feed that back into our own systems and have like the broker or partition level data breakdown, which then helps us with balancing these clusters automatically, or scaling them up and down automatically. And some of the more recent features we just launched, like around that, are all using the same data. This is all the same data flowing like into all these different use cases. We don't have to re-instrument our systems to do all these different things. And the last one, of course, we already talked a little bit about this, is troubleshooting. So understanding different request types and versions of clients, which then help us identify when there's like certain patterns that are a little bit odd with certain client versions. Now, the really like the powerful thing about this is that all our customers, our engineers, and the business, they all have access to the same data. So it really limits some of the inconsistencies. There's no question of like, oh, does this data match some other one? No, they all rely on the exact same data, which makes this very easy to explain to customers when we have to drill down into some oddities. Like, we don't have to go back and figure out, like, where did this data come from? Like, how was it being used, etc. And really, like, being able to expose all this data, like different facets of the same data for all these different use cases, we can do that without compromises by using this infrastructure, because we can have production grade APIs. They're low latency. We can build data products, and we can provide ad hoc tools to look into this data. So how do we do this? Well, of course, like, we have to embrace high cardinality. It wouldn't be possible to support all these different use cases if we didn't have these very fine-grained breakdowns of all this data. And embracing high cardinality is important, so we can get these cross-cutting dimensions for a high-level product and a business understanding. And we may have more customer-centric dimensions that we break these down by. And then, last is also like having more like the more physical, application-specific dimensions that help us with our operational visibility. And really, the key to that is really getting the data in the first place. I mean, that's probably one of the biggest challenges of, in getting this all up, is to get the data in the first place. So we had to provide a foundation for our teams to collect all this telemetry, and we didn't want them to have to go and re-instrument all their existing applications and have yet another system that they had to worry about, or yet another collection agent or things like that. So what we did is basically we wrapped around like some of the existing ones that we already had, and align on some of the standards so that we could have some standardization both on the wire format and also in providing some guidelines and consistency across tagging to all our different products. So for anything that was existing, we kind of mapped all these things into these conventions, and any new things we could ask people to follow these new conventions to make this easy to reuse this data across all these different projects and use cases. And how we do that? Well, one thing that we embrace is really some of these open standards, like Open Census, we started 2 years ago, and now Open Telemetry. So we're basically using that as our wire format in our infrastructure. It means that for existing services, they can use the wrappers that we built for some of these things. And for new services, they can just directly use some of these open SDKs and send the data directly into our Kafka cluster without having to go back and rebuild and use something custom. We can use all the off-the-shelf tools that exist out there for observability to collect all this data, which means we not only get metrics, we also get traces, and we can start using that across all the different products. These open standards also provide some conventions, some semantics that we follow, which is important because then we don't have to have all these discussions around how we should like name things. I mean, we can follow all the conventions that they already provide, and then that helps like make it easy to use this data across all the different products. And lastly, like because we're only collecting this data once, we instrument the services once, and then can funnel it into all these different tools. It means that we have consistency across the tools, whether it's like putting the data into Druid or BigQuery or some other monitoring system. They all like rely on exactly the same data, which means they're consistently across each other. And one of the important things is that our engineers, our teams didn't have to give up on their existing tools. They could continue using the tools that they had for this data that we're collecting, and then transition seamlessly between whether it's using their existing dashboards for alerting and monitoring, or then going and drilling down into the more fine-grained data into Druid and get do some more complex analysis using SQL for some of these high cardinality metrics or high cardinality events where there isn't, it may not make sense from a cost standpoint to send this to a third-party provider, or it doesn't make sense to retain this data for very long in our data warehouse. So that's where things became quite powerful, and we didn't have to reinvent a lot of things, and everyone can keep using the tools they have, but we at the same time we also get the ability to get some of the data in-house and use it for all these other use cases. So with that, I'm going to hand it over to Zoe, who's going to talk a bit more about, hinted on cost a little bit, like, some of the things that she's been working on is kind of how do we keep this this infrastructure in check so that we can continue providing the low latencies and at a pretty cost-effective, in a pretty cost-effective manner to all our internal and external customers. Thanks, Zoe.
Okay, thanks, Xavier, for going over how we use Druid at Confluent. I'm going to continue with some of the optimization techniques that we used to scale our cluster. So first of all, why we need to scale? The reason is that we have growth, as Xavier showed previously. Our growth is not, we don't have like a certain type of growth, so we don't need dynamic scaling. But our growth is more like gradual, and this growth comes from either onboarding new tenants or growing tenants. The tenants, they can add to their number of topics, they can expand their partitions, or they can add clients. All of this means that we have to collect more data from their clusters. In addition, over time, as we add some features and new use cases, the product team requires to collect new metrics from the clusters. And these new metrics also, they add to the number of events that we have to ingest over time. So in general, we scale for three things: ingestion, which is now we are at a rate of 3.5 million events per second, query rates, and also data volume. Per day, we use, we collect 12 terabytes of data, and we keep 7 days of queryable data in our historicals. In general, by design, Druid is horizontally scalable. That means when we have more load, we can add more resources, and we should handle the load. But there are some problems with it. It's not cost effective, and more importantly, the toil of operation and maintenance, it can be huge. So and the third one is that, especially for the query side, the increase the number of fanouts. That means increase the variance on latencies, and that's not good for tail latencies. So it's better to keep the number of nodes smaller. So we continue with some tips and tricks and tweaks that we made in the system to make it more scalable. That means with the same load, with these changes, we may need even less resources to handle the load. So the techniques that I want to present today, probably we can put them under 4 different categories of scaling principles. The first one is divide and conquer. Our queries, they are not the same. They may differ in many ways. And based on the difference in the queries or the data that these queries are reading from, we probably can partition the data and queries and optimize optimize for each partition separately. These attributes, for example, queries can have different SLOs. They can have different interval lengths. They can have different query granularity, cardinality, or they can read from hot or cold data. The second one is that we need to optimize for the bottleneck. Otherwise, it doesn't matter. That means if we spend some resources on something which is not a bottleneck, it's a waste of money. And so we need to identify the bottlenecks, which can be CPU, storage, and IOPS, and memory, and then optimize for them. The third one, which is more like a finer type of optimization, is that for each service, we can do some profiling, and we can identify where the CPUs or what features the CPU is more CPU consuming. And if we can optimize for that part. And the fourth one is that for query latencies, we should reduce the search space. And this is generally done by compaction or splitting the data source. I'll continue discussing with some of the optimizations that we did under each of these categories. So the first one is query laning. As Xavier mentioned, we have internal queries coming from engineers versus customer queries that they have some SLO on them. So the thing is that we don't want this heavy diagnostic kind of queries interfere with the customer queries. So we assign fewer threads to internal queries and also some heavier high cardinality queries. And this improved the latencies on customer queries a lot. The second one is that we observed that 90% of our queries, they read from hot data. These are the queries that usually are populating some external dashboards for the customers. So there's some continuous queries that they have very short intervals, but there are many. So we separated the hot data from cold data, and we gave more CPU resources to this hot tier, and this way they could improve latencies, as you can see in the picture. The second one is that we should optimize for the bottleneck. Here I'm going to mostly talk about some node optimizations that we made. When we started a cluster, because of some stack limitations, we had to start with R5X large nodes, which are not the greatest choice. And over time, we grew the number of historicals and middle managers. At some point, we had more than 100 historical nodes. Each of these nodes, they had 512 gigabytes of external storage. That meant high dollar cost and operation cost. First, we tried to increase the size of the external storage to lower the number of nodes. But we observed that the bottleneck here was IOPS and CPU. So we switched to storage optimized nodes with local storage. We chose I2X large nodes, which have they have big local storage. So we kind of tripled the size of the data on each node, and that reduced the number of nodes by 2/3 and the overall cost by 40%. One thing that we have to know here is that since we are migrating from external storage to local storage, the mean time to recovery can change. That's because if a node goes down in case of external storage, the data doesn't need to be reloaded from deep storage. But in case of local storage, it needs to load again. We first measure the MTTR, and then we try to reduce it by adding to the number of loading threads on the historical nodes. Also, we increase the throttle limits on the coordinator side. So this is faster. As for the middle managers, we grew to 200 R5 nodes, again high cost. So we switched to CPU optimized C59X large nodes. Bigger nodes generally they give better resource utilization, and we increased the number of worker capacity on each node. Previously, we had only one worker on a node, and we could increase it to 10. This decreased the number of nodes by 90%, cost 60%, median latency 60%, and it even gave us some headroom for growth. Okay, the other thing was about CPU optimizations, fine-grained CPU optimizations. We did some profiling on middle managers, and we noticed that 40% of the CPU is consumed by queries that are scanning from incremental segments. Incremental segments are the segments that the middle manager is still writing to them, and the data is using a write optimized data structure. So reading from them is not the most optimized thing. So we enabled the skip incremental segment. It saved CPU. But on the downside, we had to miss some data points in the latest 30 to 60 seconds of data, which was okay for us. So this is the one optimization we did. The second one is that we did some profiling on brokers, and we noticed that the authentication between brokers and other nodes, which we are using basic auth, was consuming significant CPU. So we disabled the internal auth since we already had other security measures in place on the cluster, and that also reduced the CPU overconsumption. And the third one is that there's a flag. Actually, there's a optimization on the Druid side that that it tries to sort the result set. So the data is already sorted when we want to apply the limit on it. In our case, the result sets, a lot of the result set that we get from our queries is not that big. So we tested this, and we noticed that disabling this can help us. It can vary by the type of queries and the limit, if it's big or not. So it's something worth trying in the optimizations. So the first one is reducing the search space. This is especially more important when queries have long intervals. When we have long intervals, the number of segments that we read, it can get huge. So the first way to improve this is by splitting the data source by cardinality. That's what we did. So instead of having all data in one data source, we filtered out the metrics with very high cardinality and put them in a separate data source. The reason is that we always had problem with queries that reading from this data, because we had to read from this data and then group by the high cardinality label, and the result was also big. So after doing this, it reduced the search space. So it removed some of the spikes in the latencies that we had, and it improved P95s on these queries by 30%. The second one is the feature compaction, the feature that Druid provides itself. Generally speaking, compaction can help in three ways. It can help by roll-up. It's only possible if the granularity of the queries are bigger than granularity of the data that we collect. So if our queries only read data by hour, so we don't need to keep data by minute. In our case, we couldn't do it, but maybe with some splitting data source, you can do it. And keeping the data with similar granularities in separate data sources. That's one way of taking advantage of this. The second one is that by merging smaller segments and making bigger segments, we can reduce the search space. And the third one is that by reordering the data, compaction can help with the data locality and improve latencies. For example, let's say you go to a library, you want to find all books written by an author. So if there's no order in the books, it's very bad. But when we want to have some order in the data, we should make sure that it's the right order. For example, if we sort the books by title, it doesn't help. Still, we have to go to many shelves to look for the books. So here the query is looking is giving us the author name. So it should be ordered by the writer name, right? So in our case, we tried compaction. We tried dynamic and hashed. Dynamic is faster. It reduces the query fan out because it makes bigger segments, but it doesn't help that much with data locality. So we used hashing, and since our queries they filter by metric and tenant, so we use these in the filtering. Sorry, in the hashing. So we did this, and since each compaction task works on one time chunk at a time, and our time chunk length is 15 minutes, the amount of data that we have in this time chunk is kind of big for compaction. Is 90 gigabytes of data. So we had to run some of these compaction tasks in parallel, so that we could manage with the data volume. So as for parallelization, the compaction tasks starts with some initial phase. It assigns some of the parts of the data to some indexing tasks, and the number of indexing tasks in the config is determined by max number of concurrent subtasks that we have in the config. And then we merge all of these results into the number of to some segments. And since the number of shards here is 100, we use also that many merge tasks. So the other point about compaction is that since we are very sensitive to the ingestion lag, we didn't want compaction to kind of interfere with our ingestion. So we use a different tier of middle managers for compaction. As a result, yeah, this helped with the data locality a lot and improved query latencies. And not only that, it also lowered the storage needs. This is because when we have similar data adjacent to each other, it helps with the compaction. So, and this storage reduction, our observation was that it was even better when we had high cardinality data. For our data source with high cardinality data, the size of the data source was reduced by 66%. And as you can see here, the latencies also improved a lot. So if you're interested to read about this, we just published a blog post by my colleague Harini. So you can find that. And thank you if you have any questions.
Thank you so much, Xavier and Zore. That was a fantastic presentation. If folks have questions, you can type them in the Q&A tab. I'm Charles. I work for Imply in the Docs team. Sorry, my a little bit choking up there. So the first question, Xavier had touched on this in his presentation, but Mikael was asking, is your telemetry collection a custom app or is it part of the Kafka platform? I know that you talked about that some. Is there any more detail you can add about the telemetry?
Yeah, so this is, it is actually part of Confluent platform because we use it today to collect some of the telemetry from our on-prem customers. So if you use the enterprise or the paid version of Confluent platform, that's all included. That being said, it's still primarily used for internal purposes. It is something that we'd like to open up to other use cases. I touched upon the fact that we were using different wire formats. Like we started off with Open Census and we're moving to Open Telemetry now that that's matured a bit. So I think once we kind of finish that off, that migration to the newer standard, which is succeeding Open Census, then we can make this something that we can open up to customers as well.
Thanks a lot. Franklin is asking, what are your typical deploy times for historical? They're saying that since stateful sets are updated serially, it can take a long time to roll out changes.
That is true. One of the challenges that we had, and we always try to reduce the number of historicals, is that when we want to roll them, it takes a long time. If I remember correctly, previously it was like 4 minutes, 3 or 4 minutes between roll-ups. I think we did some tuning with maybe number of threads, loading number of threads. I'm not sure. You can contact me later. But we decreased that to 1 minute per historical node.
Thank you very much. This isn't a question, but it came from Robert. He just wanted to congratulate you on the improvements, Zore, and say thank you for the interesting talk. And I agree, this was really fantastic to see what you've been able to do as far as observability and monitoring and that kind of thing. More questions? You can, we've got a few more minutes. If you have them, just type them into the Q&A tab. All right, Karthik is asking, does KSQL DB have any role at all in this data flow?
So a lot of this architecture was built up when KSQL was still very young. So we do not use KSQL DB today in this flow. as I mentioned before, we basically pipe the telemetry data directly into Druid. Are there use cases for KSQLDB? Yes. I mean, like I said, we produce all this data in a pretty standardized format. We wrote some code to support open census and open telemetry formats in Druid. We're hoping to contribute those back. But any other application that supports any of these formats or has some adapters, could presumably consume this data. So we already have other use cases for this data in-house where people are consuming this data into other systems. We're using some KSQLDB downstreams from some of that data, but not directly in this flow today.
Thank you very much. Any last questions? Xavier or Zoe, did either of you have any final statements before we wrap it up here? No pressure.
Yeah, stay tuned. We are working on more optimizations. We are working on automating our operations by Druid operator. So hopefully in the future we'll have more to share.
Yeah, and
Well,
I
we
think
definitely look forward to that.
If you want to try all these things out and see them in action, I mean, you can go on to Confluent Cloud. I think we have, you can sign up there and start playing around with it. And all these features are available to everyone. You can see them live. You don't have to pay anything extra for all these things.
Thank you very much for this great presentation, and thank you to all the attendees for joining and for your good questions. And we look forward to all the new great things you guys are doing. It's awesome. Thank you.
Thank you.